Ilijas began his education in Belgrade. He received an undergraduate and graduate degree there. Then he came to Canada, and his PhD degrees from the University of Toronto. For that PhD thesis, he received several prizes in 1997, including the Sachs Prize for the outstanding thesis in logic. Ilijas asked me to point out, and it's very important that I do so, that he is a set theorist, and has worked in a number of areas, many areas, and maybe all different kinds of set theory. But the work he's telling us about today involves applications of set theory to C-star algebras and operator algebras. I'm happy to introduce Ilijas.
Thank you, Carol. So thank you. It is a pleasure to give this talk. You see, this is a... Oh, microphone. Do you need microphone? Ah. Right. Okay, so I guess this is better. Actually, I feel funny with this, there was virtually no connection between operator algebras and the logic until maybe some 15 years ago. Then suddenly subject exploded. So what I'm going to say to do today is just choose 3 extremal points of the set of all different connections. And I'll leave it to you to figure out what is the convex closure of those 3 points, and then see what the subject is about. It is interesting to point out one connection between subjects. They are both they both have a high level of abstraction, which is maybe one of the reasons why there is a connection between them. I should say here, just for the experts, that I'm going to be lying and cutting corners here and there, and just basically going for clarity and transparency as opposed to formalism. So I may be saying some things which are kind of stretching the truth. Okay, operator algebras. What are operator algebras? Well, take your Hilbert space H and look at operators on that Hilbert space. It's important that Hilbert space is a complex Hilbert space because you need to have self-adjoint operators. I need to have a spectral theorem for those operators. Now, we say that algebra of operators is self-adjoint if it's closed and taking adjoints of its operators. Now, I should say right now that one of the most interesting applications recently was about non-self-adjoint algebras, but we go on. And I'll be concentrating on 2 different kinds of operator algebras. First, von Neumann algebras, which are closed in weak operator topology. And second is the C-star algebras, which are closed in norm topology. We import terminology from operator theory and talk about positive, self-adjoint, unitary, normal, etc. operators in the algebra A. Okay, so let's look at a abelian case first. If you try to classify the separable algebras, when I say separable, I mean separable in topology that I just defined. Well, because of spectral theorem, any abelian algebra is basically an algebra of multiplication operators on some Hilbert space. So in von Neumann case, what you have is just L infinity of some measure space. In case of C-star algebras, you get continuous functions on compact Hausdorff space. Now, if you try to classify these, in case of von Neumann algebras, you just need to count the atoms. And the number of atoms is a complete isomorphism invariant. In case of C-star algebras, classification is a bit more difficult. Right? We're talking about compact metrizable spaces up to homeomorphism. We'll come back to that point a bit later on. This is the occurring theme, you see. Von Neumann algebras have a beautiful, simple structure. Everything is clear, everything is definable, and the C-star algebras are a bit rugged. So my first reaction when I saw this was, like descriptive set theory and combinatorial set theory. I just felt at home with this notion. So in both cases, here we have equivalence of categories. Now, von Neumann algebra started in the 30s in the work of Murray and von Neumann, and C-star algebras were born some 10 years later in a work of Gelf and Nymark and Siegel, who basically axiomatized C-star algebras. So if you have a complex Banach algebra with involution, if it satisfies the so-called C-star equality, it is isomorphic to a C-star algebra. So we have, on one hand, abstract C-star algebras, on the other hand, concrete C-star algebras. This has lots of consequences, not the least one of them is that every isomorphism between C-star algebras is automatically isometry. So this is definitely not the case with Banach algebras. And since you compare to them, C-star algebras are not nearly as rugged as they are compared to von Neumann algebras. Now I should say here that it's nice that I'm going after Francois, because there are many parallels between his talk and my talk. This slide is really about definable sets. But I guess model theorists can see that. If you're not model theorist, just ignore what I say. So if you have operator algebra A on Hilbert space H, then n by n matrices over A are also going to be operator algebra over space H to the n. And we say that a linear map is positive if it sends positive operators to positive operators, and it is completely positive if each of its amplifications maps from mn of A to mn of B also sends positive operators to positive operators. Now, this is important for various reasons. One of them is that each of the operator algebra categories can be considered as a category in different ways. You can look at star homomorphisms as morphisms, but you can also look at completely positive maps. So you actually get different categories with same objects. Right. So as I said, I'm going to present three different applications. So here is application number one, which has to do with classification of separable operator algebras. I'll be concentrating on C-star algebras most of the time. Well, mostly because I don't have as much to say about von Neumann algebras as I do about C-star algebras. We say that algebra is amenable or nuclear if it is inductive limit of matrix algebras. But inductive limit in the category of completely positive maps. So this is a fairly wide class of algebras. And separable amenable von Neumann factors, actually algebras, are essentially classified by the work of von Neumann, Kohns, and Hagerup, mostly. And classifying simple, amenable, unital, separable C-star algebras. You see I have many more conditions here. And even with all those extra conditions, this is not over yet. This is the subject of the ongoing Ilijas program. So one of the recurring themes here is that some machine is devised to work with von Neumann algebras. And then a couple of decades later, by work of many people, it somehow gets transferred to more rugged terrain of C-star algebras. And it works there. So this is really happening all the time. And as I said, this is still ongoing. So let me just quickly say a few things about Elliott's program. There is a functor, some sort of a K-theoretic invariant, which is now called Elliott invariant, from category of C-star algebras into category of K-theoretic invariants. And around 1990, George Eliot conjectured that amenable, simple, separable, unital algebras are classified by this invariant. And also, very importantly, he conjectured classification is strongly functorial. Now, what we mean by this is the following. On the left, we have two C-star algebras and the homomorphism, star homomorphisms between them. On the right, there are two Elliott invariants and morphism between them. So of course, morphisms go to morphisms by a functor, but this is strong classification, which means that every every morphism between invariants can be lifted to morphism between cyst algebras. Now, there were some spectacular successes in classification of cyst algebras, and many subclasses of amenable algebras were classified. But there were also some counterexamples. I believe first counterexample was by Mikael Rordam, who constructed a cyst algebra which has a finite and infinite projection, which is just something that does not happen in von Neumann algebras. Basically, it goes back to von Neumann himself, who proved that there is no such thing in the category of von Neumann algebras. All right, as I said, a few people found counterexamples to Elliott's conjecture. Now, how do you find counterexample to some conjectural classification? Well, you find two algebras and say, well, look, they have the same invariant, but they're not isomorphic. But how to prove they're not isomorphic? Well, you find another invariant. But then one can just simply add that to the invariant and say, well, maybe this works. This actually happened a couple of times. But how do you prove the ultimate non-classification result? This is where logic comes in. So let's just step back and look at some abstraction of what abstract classification means. Recall, a topological space is Polish if it is completely metrizable and separable. And analytic sets are continuous images of Borel sets. So this is unfortunate and confusing terminology, I guess. But interestingly enough, in both operator algebras and logic, analytic means the same. It means this, which shows that there were connections back to Berkeley-Leffers, I guess, in Mackey in the 50s and 60s. Now, equivalence relation is analytic if it is analytic as a subset of the plane. And thesis number one is that almost all classical classification problems in mathematics are just dealing with analytic equivalence relations on Polish spaces. I'm saying almost all, so you cannot find counterexample to this, because if you say, well, how about this one and this one? Almost all. And also, in almost all cases, the space of invariance is also a Polish space, and the computational invariant is given by a Borel measurable. So when you have this, then you can actually, you have a concrete mathematical statements about classification of something by certain kinds of invariants. In joint work with Andrew Thompson and Asger Tornquist, we proved that both of these theses are confirmed for cyst algebras. So this wasn't too difficult, but it wasn't really very easy either. And I should say that in thesis number one, you have some classification problem. You want to find a Polish definable model for that classification problem, and that model is by no means unique. But there is a curious phenomenon that whenever there is more than one model for a classification problem, they all turn out to be equivalent in a very concrete way. So now, the question of why is that so is really more philosophical than mathematical. At least I don't see a natural formalization of that. But here, it was first difficult to find a model, and then we found several, so that there are three substantially different models for several cyst algebras, but they're all equivalent. Now, how do you compare different equivalence relations? So let's say that E and F are equivalence relations on Polish spaces X and Y. Mackey defined the following notion: E is smooth if there is a Borel measurable map into the reals, so that in equivalent, so that two points are related if and only if their image is the same. And now natural abstraction of this definition was given by several set theory distributions. We said relation E is Borel reducible to relation F. If there is a Borel measurable map such that 2 points in domain are equivalent if and only if their images in the range are equivalent. Now, this relation says that, there are different ways to interpret it. One of the ways is to say that if you can somehow classify F, then by just composing functions, you also get classification for E. So E is not more complicated than F. Right, so at this point, we actually have a concrete mathematical foundation, right? So we have a Borel model for separable cyst algebras, Borel model for Elliott invariants. Everything is Borel. And now just the question is how we can gauge this relation. Where does it sit in the world of different classification problems? Over the last 25 years, there was a lot of work on different classification problems by many people, but well, one of the best is no longer with us, unfortunately. Rekord died a couple of years ago, and there are quite a few very successful results showing that certain objects, certain class of objects cannot be classified in a simple way. Let me just give one example. Look at torsion-free abelian groups. Hjort and Kekris proved that when you go from rank 1 to rank 2, you get strictly more complicated isomorphism relation. And then Simon Thomas proved that when you go from rank n torsion-free abelian groups to rank n plus 1, again, complexity increases. And even more remarkably, his proof actually uses tools which are coming from operator algebras, Hoppe superrigidity. So we have a two-way street here between logic and operator algebras. So this is obviously what we're hoping for, right? We were hoping to somehow say, well, look, amenable cyst algebras are strictly simpler than arbitrary cyst algebras or exact cyst algebras, and they are strictly simpler than maximal this or that. And there was a lot of work in this subject. And one important thing to keep in mind, if you're trying to solve some problem, it sometimes helps if you tilt your head a little bit and just look it slightly from a different angle. And actually at this point, I'll have to ask all of you to tilt your heads because you see the map of all different relations. Is this readable at all? It simply doesn't fit on one page. And this is only classification points which are directly relevant to operator algebras. Now, what is important here is that the vertical dashed lines are strict boundaries. So what is to the left is strictly simpler from what is to the right. So in particular, classification of separable amenable cyst algebras is more complicated than isomorphism problem for countable abelian groups or for any countable structures. And on the other hand, it is strictly simpler than isomorphism of separable Banach spaces. It's somewhere in between. And well, okay, I should say that I'm not mentioning all the names. This is work of many people, not only 3 of us. So there were some things that we could not prove. So quite a few arrows in this picture were not known to be reversible. And then 2 young colleagues showed up, and this is what they did. So it's Marcin Sabok and Joseph Zielinski. So what they proved is that the maximal orbit equivalence relation for Polish group actions, which is strictly more complicated than any classification of separable cyst algebras, is actually Borel reducible to homeomorphism of compact metrizable spaces, which is really abelian separable cyst algebras. So the whole picture collapsed. Not the whole picture, but a big part of the picture collapsed. Now, what this shows is that Borel reductions are really too coarse to really gauge complexity of isomorphism of cyst algebras. And one needs a finer tool. Now, remember, we have completely ignored the functoriality. So it would be good to develop some version of Borel categories reduction between them. And actually, my student Martino Lupini has some preliminary results in this direction. But it's time to move to my topic number 2, which is in a completely different range of this set of different applications of logic to operate algebras. So it's a Calkin algebra. So take infinite dimensional separable Hilbert space complex. Look at B of H, all bounded operators in space. And look at the only ideal of that algebra, the ideal of compact operators. Take a quotient. That is called the Calkin algebra. Now, you may wonder, why would one want to construct such a monstrous object? I mean, this is really monstrous. It's a great source of counterexamples to all sorts of things. Well, the fact is that actually this is a very useful algebra, and it serves as an ambient for study of separable cyst algebras and then, single operators. And there are different theories of extensions of cyst algebras. And Calkin algebra and also other so-called coronal algebras, which you're going to see in a few slides, serve as a great magnifying glass for studying separable cyst algebras. But concretely, Brown, Douglas, and Fillmore, in a seminal work in 1977, studied equivalence of different operators with respect to compact operators, and proved many results, and this was really highly influential work. And at some point, they came at a point that they could not resolve. So here's the problem. If you look at unilateral shift on the basis of a Hilbert space and send it to Calkin algebra, it becomes unitary. We'll going to S here. So the question is there automorphism of the Calkin algebra which sends S to its adjoint? Now, this is the simplest question of this sort that BDF could not solve. What one can relatively easily show is that there is no inner automorphism which does this. So S and S star are not unitarily conjugate. This is a Fredholm index argument. So because questions seem difficult, they ask easier question. What about outer automorphisms? Are there outer automorphisms of Calkin algebra at all? And still, this question resisted any attack for some 30 years. Now, to see why question was so difficult, we have to move back in time some 20 more years. So, and look at the abelian version of the problem. So it may not be obvious that this is a abelian version, but trust me, I know what I'm doing. So, theorem of Bolter-Rudin from 1956. If you assume continuum hypothesis, then Boolean algebra, power set of natural numbers modulo ideal of finite sets, has 2 to 2 to Aleph0 automorphisms. Now this is a lot of automorphisms. It's more automorphisms than there are elements in the algebra. Second, Chek-Stone remainder, beta n minus n, has 2 to 2 to Aleph0 automorphisms. And 3, cyst algebra L infinity mod C0 has, you guess, 2 to 2 to Aleph0 automorphisms. Now, the fact that you have the same number in each of the statements is not accident. Of course, this is really the same statement. You see, first, Boolean algebra, the second space is simply Stone space. So you have Stone duality. And also between compact outer spaces and the abelian cyst algebras, again, you have Gelfand-Naimark duality. So this is really one result, but presenting itself in 3 different bases. Now, I'm supposed to present one complete proof in my lecture. This proof is 68 years old, so it's near retirement, I guess. So I can present it in 30 seconds. I think it's right for something like that. So let's go. Well, first, our big assumption, continuum hypothesis. We can well order the power set of n modulo finite in type IL1. You can see that I'm proving the second, the middle formulation. Now, second, this Boolean algebra, P of n mod finite is countably saturated. Now, what that means is that whenever you have a countable system of equations and inequalities with parameters in that algebra, if you can solve every finite subset, then you can solve the whole thing. All right. So now I take my two copies of P of n mod finite, the right copy and left copy, or it's left copy and right copy. What I do, well, I pick element here, send it over there, then pick something here, send it over there, and just go back and forth. And now all that I have to take care is that at every stage, what I have is a partial isomorphism. So I have isomorphism between countable subalgebras. And now, okay, so I'm at some late stage in my construction. Look at the next element in my ordering. And now look at all the formulas that it satisfies with parameters that I have so far. So this is a countable system of equalities and inequalities. I use my partial isomorphism to send that system to the other side, and then by countable saturation I can find a solution. And that's the place where I send my element. And then I do the same thing this way. Right? So this is called back and forth method of, it's really forth and back, I guess. I'm not sure how terminology was chosen, but it works. So this way we get isomorphism. Now, you see, continuum hypothesis was really important because this algebra is countably saturated, or some people call it IL1 saturated, but it's not IL2 saturated. It was actually proved by Howard in 1908 that you just cannot go past IL1 if you do this. So Rudin's proof doesn't work without continuum hypothesis, but it doesn't mean the theorem is false. Right? So let's see what is going on. So just zoom out a little bit and see what is the right context for this. So this is very abstract definition. We have two structures, M and N, of the same signature, and we say that automorphism of N is trivial if it can be lifted to some sort of morphism of M into itself. Now, in our situation, there are always going to be at most continuum many trivial automorphisms, which is less than 2 to 2 to all of 0 automorphisms. Right? And in one of the seminal works of Sakharov and Shella, which was done roughly around the same time that Brown and Aug15Fri asked their question, he constructed a model of ZFC, or rather, he proved that if ZFC is consistent, and remember, we'll never know whether ZFC is consistent, then so is ZFC plus the statement that all automorphisms of P of n mod finite are trivial. And therefore, this is exactly the opposite statement from Rudin's conclusion. Now, Sherlock's model is a finite support iteration of Oracle CC forcings of cardinality IF1, and the continuum is IF2 in this model. Now, if you take that and take nice Gödel's constructible universe in which continuum hypothesis holds, well, it's clear that Gödel's model is more natural, right? So this is kind of weird forcing extension. And now the question is, does that mean that really we should go for Rudin's conclusion? Well, now there are two schools in set theory, and I definitely belong to the other one. So I will try to justify this rigidity and actually argue that there are canonical models in which these conclusions hold. Forcing axioms. So if you have a class of compact counter spaces, you can consider strengthening of the bare category theorem, which says that whenever you have IF1 many dense open sets, their intersection is still dense. Now, exercise is that even if you just take some compact metrizable space, like 0, 1, continuum hypothesis fails if it follows from forcing axiom. Now, you may have seen Martin's axiom before, but there is a maximal forcing axiom, proved by Former, Magidor, and Shala in 1988, that modulo some very large cardinals. There is a maximal class K for which forcing axiom of K holds. And this is so-called Martin's maximum, or MN. Now, okay, so it's probably the strongest forcing axiom, but you will quite often hear set theories talking about MM++, which is strengthening of MM, but let's not go there. So this is a very nice canonical statement, and it was proved that Shell's conclusion that all automorphisms are trivial actually follows from MM. This was a result of Sherlock's reference. And there were lots of results of the form forcing axioms imply that this or that is region. All right, now let's go back to C's algebras. Phillips and Weaver proved in 2006 that the continuum hypothesis implies Calkin algebra has 2 to 2 to L0 outer automorphisms. And so this is a version of analog of Rudy's result. And now you may wonder, why did it take so long, 30 years, to prove? You know, proof, if you just look at the proof from afar, it looks like Rudy's. It is, you just enumerate and, back and forth it goes. But it is immensely more complicated. This is actually probably the most complicated continuum hypothesis construction that I'm aware of. And there is a reason for that. There is a mathematical reason for that. So here's the reason. It was proved in joint work with my default co-author, Red Hart. Calkin algebra is not countably saturated in the appropriate logic. We'll come to logic in part 3. Even more interestingly, Calkin algebra does have certain remnants of countable saturation. It has some, it is countably saturated to some extent, and actually quite a few important results hinge on that. The Kolescu's double comitant theorem or Kasparov's technical theorem, they both have as important component certain countable saturation property of the Calkin algebra. And now finally, Martin's maximum implies that all automorphisms of Calkin algebra are trivial, and therefore they're inner. I should say a few words about the proof. It's long. And roughly it goes like this. So first you break down your Calkin algebra into algebras of operators which are quasi-diagonal with respect to some fixed partitional Hilbert space into finite dimensional subspaces, and prove that restriction of the automorphism to each one of them is implemented by unitary. Use MN for that. And now what you have is a family of pairs, so it's partition of Hilbert space into finite dimensional subspaces and the unitary, and they're coherent because those unitaries are implementing the same automorphism. And then you use MM once again to uniformize this coherent family of automorphisms and produce a single unitary. Now this second part is something that I don't understand very well, although it's been a phenomenon that was observed maybe some 30 years ago, that somehow forcing axioms trivialize certain cohomologies. But anyway, back to Brown-Douglas-Filmer question. MM implies that no automorphism of Calkin algebra sense shift to its adjoint, S is unilateral shift. So at least positive or negative answer to their question is consistent with theirs. Now, there are outer automorphisms, but all of them are constructed by using, by basically taking inner automorphisms and somehow twisting them and getting some non-trivial limit of inner automorphisms. I mean, Phillips Weaver automorphisms, and also there is a simpler construction due to my former postdoc, Sam Koski, myself. All of them are of the same form. So it's still, original question is still open. Is it relatively consistent with ZFC that some automorphism sense shift with adjoint? I should say here that there is a very deep result of Hugh Woodin's so-called sigma 2-1 absoluteness theorem, which explains everything you need to know about certain kind of statements, like statements that this question is asking about. And it basically says that if you want to construct something like that, you might as well use continuum hypothesis. Basically, if anybody succeeds using some weird axiom, you have a good chance of using CH and constructing it. There is no analogous meta theorem for forcing axioms. And actually, some of the most interesting and deepest questions in combinatorial set theory have to do with that. But that's not subject to my talk. Let's just go on. As I said, other coronas. So Calculus algebra is only one in the family of these monstrous quotient algebras. To every non-unital C-star algebra, one can associate so-called multiplier algebra, which is the largest C-star algebra which is unital and which has your algebra as an essential two-sided ideal. And then if you look at the quotient, now this is non-commutative analog of the Check-Stone compactification. So examples, well, if you have a locally compact Hausdorff space X, the corona of C0 of X is exactly continuous functions from beta X minus X. And this is actually how some operator algebras define Check-Stone compactification. Corona of compact operators is, of course, the Calculus algebra. And corona of a direct sum of unital C-star algebras is a reduced product modulo direct sum. Now, again, these algebras are quite important, as I said, as ambience for different BDF-like theories. But also, this last algebra, in the form of so-called asymptotic sequence algebra, is some sort of replacement for alpha powers. So you see, in C-star algebras, we have people who prefer to use asymptotic sequence algebra and those who prefer to use alpha power. I'm more of an alpha power person, but these are important, so they are well studied. And okay, so natural question is, what about automorphisms of these chronologies? Conjecturally, MM implies that all of them have only trivial automorphisms. This does not imply inner in general, but trivial. And continuum hypothesis implies that every non-trivial corona has lots of automorphisms. There is a lot of work on each one of these conjectures. I'm not going to try to present it all here. I'll just give you some idea by presenting two theorems and two open questions. So recently, Saharon and I proved that both conjectures are true for continuous functions on beta r minus r. Yet, both conjectures are open for continuous functions on beta r squared minus r squared. And so this is really two very different proofs, and both of them fail miserably if you increase dimension by 1. And non-abelian cases, of course, inverse, as you might guess. So it's time to, for my part 3, I have very little time, I understand.
The last statement.
Sorry?
Both conjectures are open, and what do you mean by that?
Oh, these conjectures.
Last statement.
Sorry?
They are open, I mean,
Yes.
you can't prove it, I mean, it's not a theorem, I mean.
Oh, well, they are exactly, I mean, questions, but both questions are open. Thank you, yes, right. So I'm a logician, I'm supposed to know this, but yeah, thank you. Right, I guess it's clear. Yeah. Right, so logical metric structures. So this is a kind of model theory which is very suitable for objects in analysis. And it was developed by Ben Yaakov, Bernstein, Hansen, and Syatsov, and modified by myself, Brett Hart, and David Sherman. Now, you may have more modified to be useful for operator algebras. You may have heard either one of us talk about this, and each time you hear one of us talk about it, definitions are slightly different. So, you know, functions may be evaluated in reals or just in positive reals. Maybe you're quantifying over bounded balls, maybe just over unit balls. It doesn't matter, it's all equivalent. I'm sure that 20 years from now, somebody is going to figure out what is the right definition, but for now, it works. So let's just take. So okay, I guess essentially, you replace equality with distance, and you replace quantifiers with sup and inf, and that's your logic. And it behaves beautifully. Just lots and lots of classical results go through for this logic. And okay, two algebras are elementally equivalent if their theories are the same. And theory is you just look at those sentences and then evaluate them in the algebra and then just look at the ones which go to 0. All right. So back to part 1, classification. So this is considered to be the most devastating blow to Elliott's program. Result of Andrew Toms. There are separable unital simple amenable system algebras indexed by unit interval, which all have the same Elliott invariant. And moreover, whenever you have a continuous and homotopy invariant functor, they all agree. Functor agrees in all of them, yet they're all non-isomorphic. Now, Andrew had to come up with some curious numerical invariants to distinguish these algebras. But it was observed by Lima Robert that actually no two of these algebras are elementally equivalent. So if you're a model theorist, and if you're prepared to look at AE theory of these algebras, you can see that they are just different. So there is a weird question whether for simple amenable blah blah algebras, which have same Elliott invariant and elemental equivalent, where they have to be isomorphic. Okay, so yes, right. 1 minute.
Excellent.
Yes, okay, thank you. So type is simply a set of formulas, and we said it's realized by some tuple in algebra if all of those formulas have value 0 when evaluated there. So here's an example of a type. Take automorphism, and now what I wrote here is a type of something that is a unitary, and that implements this automorphism, which makes it inner. Now, type is realized if and only if phi is inner, and type is consistent if and only if phi is approximately inner. And so it's the point norm limit of inner automorphisms. There are many questions from C algebras which are asking, well, is there amenable C algebra which has these weird properties? If not, then we have a great theorem here. And so on. So one of the reasons for those questions being open, well, unless there are theorems there, is that there aren't so many ways known to construct new amenable algebras. There are just few constructions from tensor products, cross products, inductive limits, 2 out of 3, and so on. And the question is there a different way of constructing new amenable algebras? Now this is a 6th author paper, which is coming up, so it's soon going to be available. You see, amenable C algebras are not axiomatizable, but they are characterized as algebras which are omitting certain countable set of types. So there is certain L omega 1 omega sentence which axiomatizes amenable algebras. And almost every important class of C algebras is characterized in a simple way, in a similar way. So long-term plan, this is very long-term plan, actually exactly 8 years long plan, is to use an appropriate omitting types theorem and Hankin construction to build new amenable C algebras. Right now for that you just need omitting types theorem, well, plus a bit more, but omitting types theorem was proved by the founding fathers of the logical metric structures, but for complete types. The types that we get here naturally are not complete types. So you wanted to see, well, what about, in first order case there is no difference, but what about this one? Well, it's actually quite funny. So joint result in Menachem Magid are also coming up, it's almost ready. There is a separable theory, so that set of types omissible in a model of that theory is a complete sigma 1-2 set. So this means that the question of omissibility is intractable. There is no natural omitting types theorem. And even if you have a complete theory, still that set is pi 1/2. even worse. There is a complete separable theory T, and countable many types, such that you can omit any finite subset, but you cannot omit all of those types simultaneously. Right, nevertheless, this is not relevant to cyst algebras, all the types are nice. And I finish here. Thank you.
Thank you. There are questions? Q&A.
Bring back the... Yeah, thank you. Where is George when you need him? No questions?
You told us everything, I guess.
Oh.
Okay, well, thank you again, Ilya. You could get a present
Oh, thank you.
from the local